Hi, welcome to Unit 3, Day 1, Part 3, Particle Nature and Quantization of Light. So when we think about light radiating from a source, what exactly are we thinking of? Or what do we think about? Oftentimes we think about rays of light, just a stream of rays of light radiating from the source. But that's not the case. Light is not a stream of energy radiating as waves. Instead, what we ought to think about are these little packets of waves coming from our light source. And these little packets are known as photons. And that leads to the idea that light is actually quantized, meaning it has a specific energy. And a quantum of light is a discrete little packet of that energy, and that's known as photons. Now, how did scientists discover this? There were three phenomena that supported the idea that light is quantized. Let's take a look at the first one. The first one is blackbody radiation. And that's something that you may not have heard about before, but you've definitely experienced. So this image here is showing a nail that's being heated up. And just like with most metals, if you heat them up, they'll eventually start to glow. They'll start off as like a red color, then become like an orange, and then a yellow, and then this bright yellow whitish light will emit from the metal. And scientists observed this phenomenon for quite a while, and they knew that there was a relationship between the temperature of the object and the intensity or brightness of the light, as well as the frequency of light that's emitted. So the hotter the object gets, the more intense the light, and also the object will start to emit light at a higher frequency. But they couldn't model this mathematically. They would come up with models, and those models would work for some temperatures and some frequencies of light, but not for others. And so it took them a while to sort of understand what was really going on. And actually, the person who was able to explain this was a guy named Max Planck, who was able to model this blackbody radiation by coming up with a new radical idea that light is quantized. So he proposed that light is quantized, meaning that light has a discrete energy. And that was a totally new concept. And it turns out that 5 years later, Albert Einstein was able to use that concept in explaining the photoelectric effect. So you may remember the photoelectric effect, which is evidence for the particle nature of light, occurs when you strike metal with a certain energy of light. An electron electrons will be ejected from the surface of the metal. So how does this relate to light being quantized? Well, as a particle, light should have a discrete energy. So the photoelectric effect also supported the idea that light is quantized. So far we looked at two phenomena, blackbody radiation and photoelectric effect, that both support the idea that light is quantized. Let's look at one more. The last one is the emission spectrum of elements. So in the early 20th century, scientists were studying excited gases, and essentially what it would be a gas like hydrogen or helium, and they would excite it by running a current through a glass tube filled with the gas. And so you'll notice in this image here that the glass tube, once it's excited, the gas starts to emit off light. And if you look to the image on the right, you'll see that they would analyze the light by sending the light through a prism, and that would split the light into its corresponding wavelengths. And they found that each element had its own different sort of spectrum known as an emission spectrum. And they couldn't quite understand what caused these bands and what caused them to be at these discrete energy levels. Until Niels Bohr came along in 1913, and hearing the buzz about light being quantized, he then theorized that the discrete lines of color in the emission spectrum of hydrogen is owing to the fact that the energy of an electron is quantized. So what do we mean by the energy of an electron is quantized? So let's take a closer look at the emission spectra for something like hydrogen um, and the hydrogen atom. So when a hydrogen atom is excited by that current, the electrons in that atom will jump from what's called the ground state to an excited state. So they'll go from a lower energy level to a higher energy level. Now, there's a well-known fact that things tend toward lower energy, the same concept of a ball rolling down the hill. So the excited electrons do not want to stay in this excited state, and instead what they'll do is they'll drop down, as shown here, to a lower energy level. As the electron drops down to a lower energy level, they emit light. So they lose this energy by emitting light. And this light is captured in the emission spectrum. So in order for the emission spectrum to produce this specific pattern, instead of looking like a rainbow, they're just specific bands, the electrons must exist at discrete energy levels, meaning that an electron can be at the first or the second energy level and the third or the fourth, but it can't be between the fifth and the fourth, for example. It has to be on that energy level. And so that led to the idea that the electron has quantized energy as well. So this sort of helped further support the idea that the light, which is being emitted by the electron and also being absorbed by the electron, is also quantized. So let's sort of recap some of the things that came about in about the span of 100 years about electromagnetic radiation, starting with Thomas Young, the double slit experiment, which demonstrated the wave nature of light in 1801. And about 100 years later, Max Planck came up with the concept that light is quantized. And then 5 years after that, Albert Einstein explained the photoelectric effect as evidence for the particle nature of light, and that also further supported the idea that light is quantized. Finally, ending with Niels Bohr, who in 1913, analyzing the emission spectrum, said that the energy of electrons is quantized, which again further supported the idea that light itself is quantized. Okay, so let's take some notes here. So first thing, the three phenomena that support particle nature and quantization of light are blackbody radiation, photoelectric effect, and the emission spectrum. Make sure you get these in your notes. Secondly, a quantum of light is a photon. So each photon contains a discrete amount of energy. Let's talk about that energy now. So the energy of a quantum of light is represented by this equation, E equals h nu. E standing for energy, and that's measured in units of joules. H is Planck's constant, which is 6.626 times 10 to the minus 34 joules second. And then the nu is your frequency, which is measured in hertz. So we have this equation for the energy of light, but remember we also have the equation for speed of light, which relates frequency to wavelength. So we can use these equations, the speed of light and the energy of light, to derive an equation that relates energy to wavelength. Since this equation relates energy to frequency, we can just get another one that relates energy to wavelength. And we'll do that by first solving for frequency using the speed of light equation. Then we can plug that value in for our frequency, and we get the equation energy is equal to Planck's constant times speed of light divided by the wavelength. Okay, so let's revisit CFU to see which of the waves has the greatest energy explained. So now that you've seen the equation that relates energy and wavelength, you can now tackle that question. Pause the video now. When you press play again, the answer will be revealed. All right, so the answer to that is A, because it has the shortest wavelength, or you can say it has the largest frequency. In either case, as frequency increases, energy increases, and as wavelength decreases, energy increases. Okay, now you're going to try these CFUs, 4, 5, and 6. Pause the video, and when you press play again, the answer will be revealed. So for CFU4, they're asking how much energy in joules does the light from CFU3 have? And for that, we need to know the frequency, and we have Planck's constant. So we plug in the frequency from CFU3 into the E equals h nu equation, and we get the answer is 3.37 times 10 to the negative 19 joules. For CFU5, they're asking how is the wavelength of light related to the energy of light? Is it direct or indirect? So if you look at the energy is equal to Planck's constant times speed of light divided by wavelength, you'll see that if you increase the wavelength, which is in the denominator, that's going to lower the value of energy. So they are inversely or indirectly proportional. Last CFU, which would carry more energy, a radio wave with the wavelength of 10 to the third meters, or light that has 5.3 times 10 to the negative 28 joules of energy, and show your work. In order for you to compare them, you have to convert either the wavelength to energy or the energy to wavelength. And in my case, I converted the energy to the wavelength into energy by plugging it into this equation. And since the wavelength was in meters, I did not have to convert it. But if it was in nanometers, I would have to convert it. All right, so that's it for this video. And that's it for this series. Have a quality day.